Greetings, math fans. All right, this is day 5, and today we're going to talk about more limits, but we're going to talk about limits involving infinity. So limits involving infinity. Okay, and basically when something involves infinity, really what we're talking about is called end behavior. Okay? All right, so let me just do some examples here, and we'll talk through them here. The first one is limit as x approaches infinity of 1 over x. I want you to think about what's happening here. What happens when x gets really big? Okay? Well, when x gets really big, doesn't that whole, it's 1 over some huge number, doesn't that go to 0? Okay, does that make sense? I hope. Okay, so when, again, just kind of think about it. Put a big, really big number in there, and what happens? It goes to 0. All right, let's try, this is actually just the same thing. It says when limit as x approaches negative infinity. Well, that's like saying 1 over, negative a billion. Well, doesn't that also go to, of 1 over x, of course. Does it also go to 0? Okay. Second example, limit as x approaches infinity of 2x squared plus 5x minus 3 over 3x squared minus 2x plus 8. Now I want you guys to think about it. As x gets bigger and bigger, these values right here really don't matter, because what's happening is that when you square some number and it gets bigger and bigger, you square it, the squared number versus just the number itself becomes more and more insignificant, or I should say the small number becomes more and more insignificant as the number gets bigger and bigger, right? Because if you square like 10, it becomes 100. But if I square 100, it becomes 10,000, right? So it becomes less significant that 100 versus 10,000 versus the 10 versus 100, right? It becomes less significant. So the deal is, I don't even have to worry about that, because it doesn't matter as the number gets bigger. Really what I'm looking for is I'm looking for the highest degree coefficients and for the top and the bottom, and actually the highest degree. So truly this problem is limit as x approaches infinity of just 2x squared over 3x squared. Okay, so the other stuff again is not relevant. And then of course x squared over x squared, that just cancels, and we wind up getting really the limit as x approaches infinity of 2/3, which is just 2/3, right? Alright, so let's do another one here. These are pretty easy though, right, to kind of figure out what we're doing here. Limit as x approaches infinity of 5x squared plus 7x minus 3 over 2x minus 7. Well, again, I'm going to take this guy here, the 7x minus 3 and this minus 7 have no relevancy at all once x gets really big. So I take the highest degree on top, so it's 5x squared. Highest degree on the bottom, 2x. And this is still the limit as x approaches infinity. And I can rewrite that as limit as x approaches infinity of 5x over 2. Well, what happens is x gets bigger and bigger. Well, this goes to infinity. Okay? Just for the heck of it, if this whole problem started out with a negative, so it was negative 5x squared blah blah over 2x blah blah, what would this go to? It will be, well, negative 5x over 2, and x goes to infinity. Doesn't this go to negative infinity? Okay, so just kind of keep that in mind. Fourth one is the limit as x approaches infinity of 3x squared minus 7x over 4x cubed minus 6x minus 7. Well, again, this stuff really doesn't matter here, so we're going to say that's equal to limit as x approaches infinity of 3x squared over 4x cubed. Okay, so we can simplify that. It's limit as x approaches infinity of 3 over 4x. Okay, what happens when x gets really big? Well, it goes to, right, then it's 3 over some huge number, which is 0. All right, fifth example, limit as x approaches infinity of negative 5x squared minus x over 2x plus 3. Okay, well, that's the same thing as limit as x approaches infinity of negative 5x squared over 2x, which is just negative 5x over 2, and it's actually the same thing as this one here, right? So it's equal to negative infinity. Negative infinity. Okay, no big deal. So I'm not going to erase these. Actually, I want to cursor down a little bit because I want to write some things about them. But what we're doing is we're talking about end behavior. B-H-A-V-I-O-R. Ooh, a little rough there. Okay, end behavior. And end behavior is basically what goes on as the number as x goes to infinity. So I want you to think, math fans, what else have we done that kind of thinks a little bit about end behavior? All right, you know, right? In other words, if I give you guys a rational function here, and the function looks like, you know, like this and this, end behavior is, hey, what's going on when it goes to negative infinity? What's going on when it goes to positive infinity? So what am I really kind of referring to? I'm actually referring to my horizontal asymptotes. Okay, so my horizontal asymptote is going to be y equals b is a, I'm going to write abbreviate as HA, horizontal asymptote of a graph of a function y equals f of x if either 1, limit as x approaches infinity of f of x equals b, or 2, limit as x approaches negative infinity of f of x equals b. Okay, so let's just kind of talk about what I wrote here. End behavior is the horizontal asymptote. So that's your horizontal y equals b, that value, okay, that when I take the limit as x approaches infinity, that limit goes to a certain value, and it's b. Whether it goes to infinity or negative infinity, it goes to b. All right, and one thing I want you guys to remember before we talk about these graphs that I just did, so here, remember, horizontal asymptotes. Let me ask you a question, not that you can really answer it on the video, but can you cross a horizontal asymptote? Okay, yes, you can. You can't cross a vertical asymptote, but you can cross a horizontal asymptote. But the key is, with an asymptote, you approach. You can cross. I'm going to put this in parentheses. Can cross. But what happens, you can cross real quickly, right? Let's say this was an asymptote here. You can cross, but you always come back to it. All right? So let's go back to our original problems. And what I'm trying to do is I'm trying to get you guys to see which one, that the end behavior is the same thing as the horizontal asymptote. So if I go back to number 1, I'm going to do this in red here. The horizontal asymptote for this guy is y equals 0. And you guys kind of know that from back in the day when we graphed these, right? Remember, you look at if the degree on the bottom is greater than the degree on the top, it's automatically y equals 0. So that one's y equals 0. Let's go to number 4. Look at that, degree on the bottom is bigger than the degree on top, so it's the horizontal asymptote is automatically y equals 0. If the degree is the same, what do we know? Well, we just take the highest, we take those the coefficients basically of those of the highest degree, and that's our horizontal asymptote. So for this one here, horizontal asymptote is y equals 2/3. Again, it's the same as the limit as x approaches infinity. Okay, and let's look at number 3 now. Well, what happens when it's bigger on top? It goes to infinity or negative infinity. Is that correct? So remember, with those, the horizontal asymptote, well, it's none for this guy and for the same thing as that guy, right? No horizontal asymptote, because what type of asymptote was it? It's an oblique asymptote. Okay, so it's not horizontal, it's oblique. And again, just kind of looking at the problem, it's pretty easy to identify it, right? The degree is bigger on top than it is on the bottom. All right. Let's talk about a couple other problems as x approaches infinity. These are some decent problems here. Limit as x approaches infinity of sine of x over x. Now some of you going, oh man, that's really easy. That's equal to 1. Boo! Math fans, you have to be so careful. That is great when x approaches 0, because that's what we learned back in the day. Remember, we used the squeeze theorem to figure out sine of x, limit as x approaches 0 of sine of x over x equals 1. All right, so that is not correct. It's not equal to that. What I want you guys to do is I want you to think logically a little bit. What, as opposed to even graphing this, what happens, let me just write this problem over again. Limit as x approaches infinity of sine of x over x. What happens at sine of x as x gets bigger and bigger? Doesn't it oscillate? Doesn't it oscillate between -1 and 1? Okay, so it doesn't really get that big, it doesn't really get that small. And then I want to think, well, what happens when x gets really, really big here? Well, if x gets big, it's like saying a number between -1 and 1 over some huge number. So what is even 1 over some huge number, or -1 over some huge number? Doesn't that get closer and closer and closer to 0? All right, so for this one, horizontal asymptote is y equals 0. All right, remember, the limit as x approaches infinity is the same thing as your horizontal asymptote. All right, but that's a tricky one. People always fall into the trap. They see sine of x over x and they go, oh, geez, we just learned that it's equal to 1. No, it's not when it goes to infinity. When it goes to 0, that's true. Okay, so let's try another example. Limit as x approaches infinity of cosine of 1 over x. Okay, well, again, think about it. 1 over some really, really huge number isn't the same thing as saying 1 over, if it's some 1 over big number, it's the same as cosine of 0. So it's really saying cosine of 0, which is 1. That's what it's approaching. Okay, and if you'd actually graph that, you would see there's a horizontal asymptote at y equals 1. Okay, here's another example. Limit as x approaches infinity of 2 minus x over x plus 1 times x squared. This is kind of looks complicated. 5 plus x squared. Okay, well, we can kind of break it up a little bit here, math fans. First of all, the 2 stays the same. Do you agree with that? So the 2 is itself. So then let's do the next one here. It's as x approaches infinity, isn't that just x over x? So it's minus x over x. And then what happens when x, here, look at this one, x squared over x squared, right? That 5 doesn't really matter. So we have 2 minus 1 times 1. Okay, and that gives us 1 times 1, or 1. What happens if it goes, let's do that same problem here. Limit as x approaches negative infinity. Well, what happens? Is it the same thing? It's still, you still take the highest degree, so it's x over x, and then x squared over x squared. So my point is, does it even change? No, it actually doesn't change. Because it doesn't matter if it's going to a negative or positive, it's still 2 minus 1 times 1. 1 times 1 is 1. Okay? Alright, let's keep going here. Limit as x approaches infinity of x sine of x plus 2 sine of x over 2x squared. Okay, so what I know here is I can kind of split this up first of all, math fans. Okay, because remember some of the first thoughts of limits, right? You can break it up, and in this case here, I can this is addition, so I can just do the sum rule, and so I can say limit as x approaches infinity of x sine of x over 2x squared plus limit as x approaches infinity of 2 sine of x over 2x squared. Okay, and then I can write this, put over here limit as x approaches infinity, and that x cancels with that x squared, so I get sine of x over 2x plus limit as x approaches infinity of, we can cancel that, sine of x over x squared. Well, don't you guys agree this is the same thing as sine of x over x, right? It's just a 2 on the bottom. So this is getting, again, really huge, and this is going between negative 1 and 1, so isn't that just equal to 0? And this is the same thing, right? It's getting really huge in the bottom, and that sine of x is fluctuating between negative 1 and 1, so it's plus 0. So my answer is 0 for that one. All right? But again, don't make the mistake. So remember, limit as x approaches 0 of sine of x over x, that's 1. Limit as x approaches infinity of sine of x over x, that's equal to 0. All right, not too bad. All right, let's talk about vertical asymptotes. So let me give you an example here. Y is equal to 2x plus 8 over x plus 3. Okay, do you remember to find the vertical asymptote? You set the bottom equal to 0. So x plus 3 equals 0, x equals negative 3. Okay, what's the horizontal asymptote? So that's the VA. And let's just talk about the HA, the horizontal asymptote. Right, that's just going to be 2x, y equals 2x over x. So y equals 2. That's the horizontal asymptote. All right. You guys are going to have to be starting to graph things very, very accurately, and sometimes it's difficult to graph. The key, especially with rational functions, math fans, is you have to start drawing your asymptotes, get those asymptotes correct, and start picking points around the asymptotes to get a general idea of what the graph is going to look like. All right. So for this problem, I think it's good to, if I want to describe the behavior on either side of the vertical asymptote. So describe the behavior on either side of the vertical asymptote. So I think, again, not a bad idea is plot some points, and your vertical asymptote is at negative 3. So that's kind of like a base point. It's like my center point here. Of course, it's undefined here at an asymptote, right? Vertical asymptote. So I can pick, negative 4, and I can pick negative 2. If I pick negative 4 and I plug it in, and again, this is on either side of that vertical asymptote. It's a good place to plot it. I get a 0, and if I put negative 2 into the equation, and again I'm putting it into this guy right here, right? I put a negative 2 in there, I get positive 4. And then if I graph it, again, plot our asymptotes. So our vertical asymptote is x equals negative 3 and y equals 2. Alright, and then so it's negative 4 comma 0, so I'm right here, and negative 2 comma 4. So this kind of helps you realize is what the graph is going to look like, and this graph is going to look something like this. Again, you're kind of hugging the asymptotes, so be a little neat about it. Okay, and that's what your graph is. So it just kind of helps you out, but you can see what's our, the horizontal asymptote, right? That's the end behavior. So if I would have actually set a problem like the limit as x approaches infinity of 2x plus 8 over x plus 3, well, what happens? What's going on? This is going closer and closer and closer to this value of 2. Okay, and there you go, 2x over x, which is 2 over 1 or 2. So that's what the horizontal asymptote is again your end behavior. Okay, the last thing I want to talk about today is something just called end behavior model, and that's actually pretty easy. So it's finding end behavior models. Okay, and someday, if you are a really good mathematician, you might become an end behavior model. It's a very high-paying job. I'm just kidding. Okay, so if I give you guys f of x is equal to 2x squared plus 7x minus 3. Okay, I'm going to call this EBMs. EBM, end behavior model. Okay, it's actually really easy. An end behavior model just means, kind of like when we're finding the asymptotes before, math fans, or when something went to x went to infinity. This really doesn't matter as the number gets really big. Okay, so the end behavior model, it's really a power function for this one. Sounds kind of fancy, but truly the end behavior model is f of x equals 2x squared, because this doesn't matter. And that's really what my graph is going to look like. So this is the deal. If I would actually graph 2x squared plus 7x minus 3, and I graph 2x squared, just 2x squared, okay, initially it looked like the same, but if I would pick a point out, 10,000, 100,000, a million, a billion, a trillion, the numbers actually would get really close to each other, and that 7x minus 3 would not be significant at all. All right? So let's try another one here. I mean, that's pretty easy then. You're just ignoring that 7x plus 3. So another one here. If I said f of x is equal to 3x squared minus 4x plus 5 over x squared plus 4. Okay, and if I look for the end behavior, again, this is out of here, and this is out of here. I don't really worry about that. So my end behavior model is going to be f of x equals 3x squared over x squared. So f of x equals 3. Okay, and again, that's my horizontal asymptote, isn't it? Y equals 3. So it all kind of comes into play. End behavior model, horizontal asymptote, limit as f of x approaches, or as x approaches infinity or negative infinity. It's all end behavior. Okay, so let's keep going here. F of x is equal to 2x squared minus 7x plus 4 over 3x cubed plus 4x minus 2. Okay, and my end behavior model is going to be f of x. Okay, I'm just going to look at 2x squared over 3x cubed. So you guys agree my end behavior model is going to be 2 over 3x. Okay, and what's my horizontal asymptote for this one? It is y equals 0, of course, because as x gets right, the degree on the bottom is bigger, so it's automatically y equals 0. Okay, so far so good. Alright, so now what I'd like to do, math fans, I'd like to just show you real quickly on your graphing calculator the model we just created. Right, this is our original function, and this is our end behavior model. Just to kind of show that it really is the same. It may look different in the beginning, but again, it's end behavior, so what happens as we go farther out. So let's pull out my virtual TI here, and let's type our equation in. Okay, so we're going to do y equals, make sure you use lots of parentheses, right? 2, and by the way, this is not a way to prove end behavior. Alright, you always, when I ask you to find it analytically, or I ask you to find it graphically, that means you actually draw a nice graph. You don't use your graphing calculator to plot points. Okay, sometimes if you can use your graphing calculator to maybe draw a graph, that's nice. But analytically means do all your work, simplify things, find your asymptotes, whatever. Graphically means you draw a nice graph and you point things out on the graph. Alright, but anyway, let's keep going with this guy here. 2x squared minus 7x plus 4 divided by parentheses 3x cubed plus 4x minus 2. Okay, and then zoom 6, always a nice one. And that's what our graph looks like. You can see a better picture down here below. Okay, but our graph kind of looks like, I mean, it's definitely got your asymptotes here. Now what I want to do is I want to actually graph that along with the end behavior model. Okay, I'm going to put that in y2. So that's going to be 2 divided by, make sure you put this in parentheses, otherwise it will say 2 divided by 3 and multiply the whole thing by x. So 2 divided by 3x, and then graph that one. And if you kind of look on the bottom here, math fans, it's a little bit bigger, but what's going on? Here it's going to negative infinity, here it's going to positive infinity. Okay, you can kind of see it's a little bit different right in the beginning, right over here in this in the fourth quadrant, or in the third quadrant, and also maybe a little bit in the first quadrant, but it's actually very similar to that. But again, I'm concerned with end behavior, and that's kind of what's going on here. It's actually giving you a pretty good value of end behavior. All right. One more I want to do with you guys before we quit out of here. So let's clear this one. And here's my function. F of x equals 4x cubed minus 4 over 2x squared plus 1. Okay, and your end behavior model is just f of x equals 4x cubed over 2x squared. So f of x equals 2x. Okay, and it has no, for a horizontal asymptote, it has none. And remember, because what is it? It's an oblique asymptote. Okay? And sure enough, my friends, if I would graph this end behavior, if I would graph this function right here, wouldn't it just be y-intercept of 0 up to over 1? So that's the end behavior, is 2x, and what happens as the limit as x goes to infinity? Well, think about it, right? Doesn't it go to infinity? And sure enough, here it does. Okay, the y value goes to infinity. As x goes to infinity, the y value goes to infinity. It's whenever you have an asymptote, as x goes to infinity, y goes to some value, maybe 0 or whatever. All right. Anyway, that's it, math fans, for day 5. And again, it's we're talking about end behavior and talking about limits to infinity. All right. Have a nice day, math fans. Adios. Goodbye.